Okay, good morning, everybody. Welcome to our YouTube channel. So, for today, on this episode, we have hybridization, how you can calculate hybridization of covalent molecules. And in subsequent episodes, we'll be looking at shapes and bond angles of covalent molecules. Thank you very much. Kindly follow us. So, as we all know, before we can venture into hybridization of covalent molecules, you need to know about the shells and orbitals that make up this hybrid. For instance, you have the S hybrid, you have the P hybrid, you have the D hybrid, you have the F hybrid, and these are all orbitals of electrons. So, what do we mean by orbitals? What do we mean by electrons? Like we all know, orbitals are like a subdivision of shells. So, if I would start, we just help you with a brief recap. A shell is a region around the nucleus where electrons are in continuous or constant motion. And that was brought about by the idea of wave-mechanics model, contrary to Niels Bohr's model. While we know that inside the shell we have the subshell, and in the subshell we have orbitals. So they are basically the four defined orbitals with respect to subshell. Under the S subshell we have S orbital, P subshell we have P orbitals, where there are three atomic orbitals, Px, Py, and Pz. So we'll be using these orbitals with respect to hybridization. So talking about hybridization, what is hybridization? Hybridization is the mixing or blending of what? Atomic orbitals. Mixing or blending of atomic orbitals. Okay, just in case you do not have a full idea of what we mean by all of these shells, subshells, and atomic orbitals, you can watch out for any of our episodes that will contain that. So quickly now, you know that as I earlier said, we have the S orbital, the P orbital, the D, the F, depending on the number of them. So when we mix two or more atomic orbitals, like when we mix an S orbital, we can have 3 of this, we can have 5 of this, and we can have 7 of this. 3, 3, 1, 7. So when we mix one of S and one of P, you can see this is a mixing of S and P orbital, giving us sp hybridization, sp hybrid. So that is the meaning of hybridization. Now, basically, we'll be looking at the hybridization of common covalent compounds outlined on the board. Okay, so to start with, carbon 4 oxide, CO2, carbon 4 oxide. Carbon 4 oxide is a covalent molecule, and although there are 2 methods for the calculation of to determine the hybridization of molecules, but I'll be showing you a short trick that can help you get the hybridization without stress. So, on a basic standard, we have the VSEPR method, which is the valence shell electron pair repulsion. VSEPR, which is valence shell electron pair repulsion method. And then secondly, we have the TEP, which is the total electron pair method. Now, the particular method that will be giving us trick about is the TEP method, total electron pair method. So this idea involves using the sum of the bond pair and lone pair of electrons. So TEP equals bond pair plus lone pair. Now, what do you mean by bond pair? What do you mean by lone pair? The bond pair in a molecule or in any particular entity of matter refers to that particular number of electron pair. I believe you know that pair means 2. So one pair refers to that particular number of bond pair that is available for chemical bonding. For instance, let's take a look. Okay, before I give you an instance, when we say the lone pair is that particular electron pair that is how do I put it? Okay, that is completely filled in an orbital of a particular atom. So let's look at instances now. How do you know the bond pair and lone pair in a particular entity of matter, be it an element or in whatever compound? So let's start with an element. Let's say we have oxygen. Now, with respect to that popular question that says, what is the number of lone pair of electrons in the central atom of water molecule? Now, the central atom in water molecule is going to be what? oxygen. So now, how do you know the number of lone pair of electrons in oxygen or the number of bond pair? Now this is oxygen. Oxygen on the periodic table has an atomic number 8. That is 8 like this. And a nuclear number assumes to be 16 approximately. So now, but we do not have any business with the nuclear number. So how do you know the number of bond pair and number of lone pair? We have to write the orbital configuration. Now the orbital configuration of oxygen is going to be 1s2, 2s2, and 2p4. Yeah. So having this now, you can determine the lone pair and bond pair from the outermost shell or the outermost energy level. Meanwhile, I believe you know that these numbers represent the principal quantum number which determines the energy level. So now the outermost shell or energy level is the second shell, which is denoted by letter P. So if you are going to write the orbital configuration of oxygen, you are going to have something like this: 1s2, we have 2s2, we are going to have 2p4. And don't forget your p orbitals, and your p subshell has 3 subatomic orbitals. You can watch out for an episode that contains detailed explanation for shells, subshells under the atomic model. So this is going to be px, py, and pz. So this is going to be 1, 2, 3. With respect to law of feeding electrons into orbitals, so you are going to fill this 4. So now looking at it, in the same energy level, now, this is 2, 2. We have a particular number of electrons that is completely filled, which is the P. How many one? We have 2s2. This is completely filled. This is 1. This is also completely filled. This is 2. Now these ones are unpaired in the orbital, so they are the ones that will be available for bonding in order to become what? Stable. So in that case, these two that are available for bonding, they are the what? 2 bond pair. While this that is completely filled, not available for bonding, is what? 2 lone pair. So you can use this method to determine the bond pair and lone pair in a particular element. So now let's relate it to the covalent compounds we have outlined on the board. So I'll be starting with CO2. Now, if you can recall very well from the UTME chemistry for 2022, which is this particular year, a question was asked that what is the number of bond pair in CO2 molecule? Now, I don't know, it's not very encouraging to see that many students and candidates out there actually went ahead to pick CO2. Now we know that the shape of CO2 is drawn to be like this, O. Now normally carbon is tetrahedral when it is half filled, when each orbital is half filled. So we now have one oxygen here, one oxygen here. Meanwhile, the outermost shell of oxygen requires 2 electrons to attain stability. So that means this will take 2. Don't forget, oxygen has 2 bond pairs. So this will take 2, and this will also take 2. So now, by the time you look at it, even without even drawing this, one oxygen atom has 2 bond pairs. That means 2 oxygen atoms bonded to carbon, 4 bond pairs. Or looking at it from the aspect of carbon, carbon is tetrahedral, it has 4 bond pairs. So if it is bonding, it also has what? The same 4 bond pair. So 1, 2, 3, 4. The lines are used to denote the bond pair. So the number of bond pair in CO2 is actually going to be 4. But don't forget, I'm teaching you a trick for calculation. It is not a standard chemistry method, but it is a way to, it is not about how much of work being done, but how smart you can do the work. So kindly follow me as I show you around how to apply this trick. So I'll be taking it at random numbers. So let me be starting with the common compound. Let me start with BF3. So let's start with BF3 now. How do you get the hybridization of BF3? Look at BF3 very well. Now, there's something about the idea of central atom. The central atom is just that atom, just as implied, at the center, which is holding or reaching out to other elements of bonding. Usually, the central atom is usually more electropositive. So don't forget, electronegative elements tend to attract electron more to itself. So it's just like the electronegative element is looking for someone to attack itself to become stable. So in this case, but you can apply the logical sense to look at it. BF3, do you think it should be boron carrying 3 fluorine elements, or it should be fluorine, 3 fluorine carrying 1 boron? Definitely, yeah. I'm agreeing with you. It is going to be 1 boron and 3 fluorine. So definitely boron is going to be the central element. Now you will find out why I said you should know what the central element is going to be like. Okay, so now this is BF3. We start, the first method is calculating the number of unstable electrons before bonding, and then to calculate the number of stable electrons after bonding when it has attained either the duplet or octet electronic configuration. Don't forget, stability is attained when any element attains the electronic configuration of the nearest what noble gas. So now for boron, this is with 3 elements. So the outermost electron in the unstable element is what? Is going to be 3, right? And then this is fluorine. Fluorine is in group 7. So the outermost electron in fluorine is going to be what? 7. But then there are 3 atoms of fluorine. So that was 7 multiplied by 3. So this is 7 multiplied by 3. So this is going to be 3 plus 21, giving us 24. This is the number of unstable electrons before bonding. So having got that, now we look for the number of stable electrons. Now, the one that attains stability most times should not be the central atom, because in most cases, the central atom is reaching out to others. So in the process, the other ones coming tend to attain more stability than the central one. So fluorine is going to be the one to attain stability in this case. So now fluorine is in group 7. So if it is in group 7, it is going to attain stability by imitating the nearest noble gas, which is going to be what? Neon. And that is octet, if I'm very right. Octet structure. So what do we mean by octet? Octet is number 8. So that means fluorine is going to attain the 8th orbital configuration. So now the octet, and we have how many atoms of fluorine? 3. So that will be 3 multiplied by 8. So giving us what? 24. This is the stable electrons. 24 stable electrons. Okay? So now the next thing you do is you subtract. So how do you do that? Put your negative sign to get the difference in electron. 24 minus 24 equals 0. To give us 0. So the reason why we are subtracting is we want to get the difference in electron to give us a lone pair of electrons. So there is lone electron, 0 lone electron here. But then don't forget, the TEP method requires what? Pair. So that means you divide each by 2. A pair is 2. You want to buy your Tiger battery, say give me 1 pair, 2 pair. So that's 2 by each. So 0 over 2 giving us 0 lone pair of what? Electrons. And that's part A sorted. So now we need the bond pair. Usually I wouldn't advise, don't forget, we are talking about tricks to make it easier. So you wouldn't have to go through the process of looking for the bond pair by trying the orbital configuration. So just look at the particular compound here, and then you pick the subset, the number that is present in the what? In the molecule. What's the number here? Yeah, 3. Just 3 like you said. BF3, the subset here is 3. So the bond pair is going to be what? 3. 3 bond pair and 0 lone pair. So now let's come back to the formula. Total electron pair equals bond pair plus lone pair. So the bond pair is what? 3. The lone pair is 0. That's what? 3. Now there are 3 atomic orbitals present in what? In BF3. Now we start in order of increasing complexity. Don't forget, it is 1s, before you have 3p, or you have 5p, and then you have what? 7s. 3, 4, 5, 6, 7. So pick it in increasing order of complexity. So now 3 atomic orbitals now with s, p, p, which is what? sp2 hybridization. I believe that is very clear enough. And if you did not get that, you can go back a bit in time or watch subsequent examples that will be solving. Okay, let's quickly move down to the second example without wasting much of our time. You would actually get it a lot better in subsequent examples. Kindly concentrate. So next, BF3 is done. Let me take H2O, which is water molecule. So H2O now, hydrogen. Hydrogen is in group 1, and we have 2 atoms of it. Now 1 multiplied by 2. Added to oxygen is in group 6, 1 atom, that is 6. 1 times 2 is what? 2 plus 6, giving us 8. This is what? Unstable electron. Then looking at the one that will attain stability here, it will be like oxygen will be the central, reaching out to 2 hydrogen. So in this case, it's hydrogen that will attain stability. Don't forget, the idea is that the electropositive ones tend to attain stability than the electronegative. Okay, so now this is H2O now, hydrogen. So hydrogen is going to attain the nearest noble gas electronic configuration. The nearest noble gas is going to what? Helium. And helium will attain what? Duplet, not octet. So and meanwhile, you should note that only hydrogen will attain the electronic configuration of helium. So duplet is what? 2. So 2 times 2 atoms of hydrogen, this is going to give us 4. So this will be the stable electron here. So by the time you take the difference of the electron, you're going to have 4 lone electrons divided by 2, you have 2 lone pair of electrons. So then the bond pair, just look at the molecule, the bond pair is what? Just 2. So now TEP is going to be equal to BP plus LP, which is 2 plus 2, giving us 4. So now we take the hybrid, SPPP, which is what? SP3 hybridization. Are you getting that perfectly? Okay. On to the next. We have the next molecule. I'll be taking NH3. Okay. So for NH3, what I write okay. NH3. The next molecule, I think NH3 here. Okay, now this is NH3, ammonia, the common ammonia molecule. Now, let's start with nitrogen. Nitrogen is in what? Group 5. 1 atom. Hydrogen is in group 1, multiplied by 3. So this is 5 plus 3, giving us 8. Then hydrogen will be the one attaining duplets here. So that's what? 2 duplets, 2 multiplied by 3 atoms, giving us what? 6. Taking the difference, you have what? 2 lone electrons divided by 2, you have 1 lone 3. So then looking at the compound, the bond pair is going to be what? Bond pair is going to be 3. So having known that, the total electron pair is going to be 3 plus 1, giving us what? 4. It's still going to be just like the water molecule SPPP, which is SP3 hybridized. Okay? That is also clear. Let's move down to the next particular compound. Now, I believe at this point you should be able to solve for major covalent compounds that we know about. Okay? Let me pick BeCl2 next. Let me pick BeCl2. Okay? BeCl2, we have periodium in group 2. So you have 2 plus chlorine is in group 7 multiplied by 2. So this is 2 plus 14, giving us 16. Then this will attain octet. Don't forget, octet. So it is not essential. It's not essential. So chlorine, 2 atoms of it multiplied by 8. That's going to be 16. So there is 0 lone pair. And then how many bond pair here? 2 bond pair. The total electron pair equals 2 plus 0, which is 2. So the hybridization is going to be S and P, which is SP. So, having known that, we move now to the next molecule I have here. So let's go for PCl part. PCl5. Okay? We have PCl5. So phosphorus is in the 5. Just like a nitrogen atom, we have 5 plus chlorine is in group 7. So if we have chlorine in group 7, 7 atoms multiplied by 7 multiplied by 5, that is 5 plus 25, giving us 40. So then we have chlorine, which should be attaining octet. That will 5 multiplied by 8. Octet is 8, then 5 atoms. So that is giving us 40. So we have 0 lone electron and 0 lone pair. Then for your bond pair, come back, the bond pair is 5. So hybridization will be what? Not forget TEP will be 5 plus 0, which is 5. So hybridization is going to be SPP, that's how many? 4. And there will be 1, 2, 3, 4, 5. So this is what? SP3D. I believe you should get that. Okay? So the next compound, let's pick something different. Let's go for H3O plus and H3O plus. Let's go for H3O plus. Okay. Um, hold on. Okay, going for H3O plus. And this is more like an ionizing model before. Let me tell you the right part. So what you just do is the positive charge denotes that what electron has been lost, while the negative charge denotes that an electron has been gained. So in this case, H3O plus hydrogen is in 1, and we have 3 atoms. That's 1 times 3 plus oxygen is in what? 6, 1 atom 6. And this plus denotes that 1 electron has been lost. So what do you subtract? So this is minus 1. So this is going to be 3 plus 6 minus 1, which is what? 9 minus 1, 8. Now then this one we are playing duplets. That will be 2 times 3. Duplets to 3 atoms. So we have 6. So you subtract it, you have 2 lone electrons and what? 1 lone pair. Then come back to the bond pair. This bond pair equals what? 3. So adding it together, total electron pair equals 3 plus 1, which is what? 4. sp3, which is what? sp3. So then let me also do for a negative ion. So let's look at SO4 2 minus. Okay? So for SO4 2 minus, sulfur is in group 6. So that is 6. Oxygen is in group 6 as well. Multiplied by 4. That is what? 24. 6 times 4. Then you have 2 as the charge on top. That is, it is gaining 2 electrons. So you add it to it. So this is 6 plus 24 plus 2. That is what? 22. Then this is the attaining object. That is 8 multiplied by 4 atoms of oxygen, which is 32. So you have 0 lone electron, you have 0 lone pair. Then you come back for the bond pair, which is what? The bond pair is 4. So the total electron pair is going to be 4 plus 0, which is 4. So the hybridization is going to be sp3, which is what? sp3. So by now you should be able to calculate the hybridization of major molecules. But you should note the exceptions to this particular thing. It is NO2, even though it works for CO2, but I would not like you to use the method for CO2 because it might confuse you relative to the bond pair in CO2. If you are going to use this method, the bond pair in CO2 is going to be 2. But normally, bond pair in CO2 is what? Is 4. So even though in the calculation, look at it, CO2 will still give you the normal hybridization. CO2, carbon is 4, oxygen is 6 times 2. That is 4 plus 12, giving us 16. Then you come here, okay, octet now is 8 multiplied by 2, which is also 16. So you are going to have 0 lone electron and 0 lone pair. Then the bond pair, you come here, you say it's what? 2. 2 plus 0, that is 2. So the hybridization will be sp. Correct. But we all know that the bond pair in CO2 is what? Is 4. Please take note. So the hybridization in CO2 is sp. The hybridization in NO2 is also sp. So that will be all for today. So you watch out for subsequent episodes that will be dealing with bond angles, shape, as well as other fascinating topics in chemistry. Till we see you again. Thank you very much.